Okay, so the new unit is going to start with a new type of function called an exponential function. And we haven't talked about these yet this semester, so this is not things like x squared, so it doesn't mean that it just has an exponent. That's not the qualifications for it to be an exponential function. In fact, an exponential function, instead of being like x squared, is more like 2 to the x power. So it's basically a function with the variable located in the exponent. So an example, and we're going to kind of break down the pieces to this. An example, like I said, would be 2 to the x power. And so we would call this number 2 the base of that exponent, what is going to be raised to whatever power. And then, of course, the x is the exponent spot. Or you might see it with maybe a little more unusual base. So the base doesn't have to be a whole number. Okay, the base can be a fraction like this one, so that would of course be 1/2 to the x power. And so the first thing that I want us to do here is we're going to graph both f of x equals 2 to the x. Graph g of x equals 1/2 raised to the x power on the same graph, and then we're going to find the domain, the range, and any asymptotes of each of them. Remember, an asymptote is a boundary line that the graph won't touch or cross. A horizontal asymptote is the boundary line as x goes to the far left or the far right. So let's just say that we don't really know what the graph of either one of these looks like, and we possibly don't. So we're going to compare 2 to the x to 1/2 to the x. And then we're going to graph both of them over here. Okay. So when we don't know what something looks like, we can always do an XY table where we just pick some x's and we make sure and vary them, and then we plug them in to get the y's. So when I say we need to vary them, what I mean by that is we need maybe a couple negatives and a couple of positives. These are kind of my go-to 5 values because notice there's a couple positives, a couple negatives, and 0. You want to keep the numbers small because remember you're going to be graphing these things. So you can plug in 100 if you'd like, but that means you have to graph something that's as big as 100, so we probably don't want to do that. So let's start at the bottom. So how do I find out what I get for the y when I have x equals 2? Just plug it in, right? So 2 squared is 4. 2 to the first power is 2. What's anything at all to the 0 power? Anything at all to the 0 power, something you'll need to know, is 1. Like anything to the 0 power is always going to be 1. That was on your competency exam, if you remember right. And then remember, negative exponents give us fractions, so 2 to the negative 1 is 1 over 2 to the first, and 2 to the negative 2 is 1 over 2 squared, or 1 over 4. So remember that negative exponents get you fractions. So let's go ahead and graph this graph first, and then we're going to compare it to the other one. So we got 0, 1 here. Let's maybe go out 4 in every direction. That should be sufficient. So we've got 0, 1, we've got 1, 2, we've got 2, 4. So notice the graph goes up sharply this way. And then this way, it's just kind of slowly getting close to the x-axis. So exponential graphs tend to look like this. Exponential growth is rapid, so it's going up very, very quickly. Okay, so let's state what the domain, the range, and what we think the horizontal asymptote might be. Remember, domain is which values? X's, okay, and the range is the Y values. So if you look at this graph and you continue the arrows, right, how far to the left and right will this graph go? Kind of like a lot of the things we've graphed this semester. Yeah, forever, right? So negative infinity to infinity. But the range doesn't go down forever, right? The range seems to start at what value? Anything that looks bigger than what? 0. So it's not going to touch 0, but it is going from 0 up. And so the horizontal asymptote is actually y equals 0. Okay. In other words, if you want to, you could go ahead and draw that there's actually an asymptote here. So notice these values are going to get super, super close to 0, but never actually get there, right? They're just going to become tinier and tinier fractions. Okay, so let's use our other color, and let's compare what the graph of 1/2 to the x power is. Okay, now we're going to pick the same x values because they're small and pleasant. It's just that when you square a fraction, you just need to think about like 1/2 times 1/2, right? So 1/2 times 1/2 is 1/4. What's anything to the first power? Just itself, right? So this would be 1/2. What did I say? Anything to the 0 power is, even a fraction. 1. Okay. What about when you get to these negative exponents? So negative exponents represent fractions, right? What if you already have a fraction? What do you do to it, basically? So you flip the fraction, okay? Negative exponents create fractions. If there already is a fraction, you flip it, okay? So this will be like 2 to the first power, or just 2. This will be like this flipped squared, so it'll be 4. So do you notice that we're getting the same answers just in a different order here, right? So they're the same numbers. So using the other color, let's go ahead and graph these. So negative 2, 4 would be here, negative 1, 2. Notice they're both going to cross through that 0, 1. That's just because anything to the 0 power is 1. So what you should notice is that the shape is very, very similar, right? It's just that what? It kind of goes the other direction, right? So this would be y equals 1/2 to the x. And then using my other color, I didn't label this one, but this would be y equals 2 to the x. So let's talk about the domain, range, and horizontal asymptote of this graph. Okay, notice a lot hasn't really changed, right? So what's the domain still going to be? Like how far to the left and right are you still going? Yeah, it's still negative infinity to infinity. The range is still seeming to start where? At 0 and going up, okay? Notice I'm not including 0 because it doesn't actually hit 0, because actually there's a horizontal asymptote again at 0. So notice these graphs actually look like what to each other? Like what kind of transformation / change have we talked about this semester that these two look like has happened to them? A reflection, more specific, reflection over what? Over the y-axis, okay? And in fact, that's exactly what it was, because if you raised this to a negative power, you would get this, okay? And so remember, negative signs on the inside of the fraction, flip it over the y-axis, so it's exactly what we're doing. All right, so all exponential graphs kind of look like these, but just maybe with some changes. So just like all parabolas kind of have the same shape, but we might flip them or shift them or something like that, it's going to be the same thing for these guys. But they can change. With shifting, reflecting, shrinking, and stretching, etc. So hopefully you remember, I actually included a question like this on test 2, but hopefully you remember what these changes look like and how you'll be indicating that you need to be doing these changes. But also know one more thing here. The bigger the base, the steeper the curve. So in other words, if I asked you to visualize what 5 to the x power would look like, it would look pretty close to this blue graph up here, but what? Because 5 is bigger than 2, what would happen to the curve? It would be steeper, right? Because think about why that is, right? We'd be doing powers of 5 instead of powers of 2, so the numbers would get larger quicker. So I'm going to go over some transformations involving these graphs, but honestly, you really need to review maybe back to section 2.5 if you're a little shaky on this. Notice we've talked about transformations. This is now the 3rd time we've talked about it this semester. So like every time we talk about a new graph, we talk about how we can change that graph, and it's much the same as what we talked about before. Okay. All right, so let's look at some transformations involving exponential functions, and I'm going to handle it pretty quickly because, again, we've really already covered this back in section 2.5. So if you don't like the speed at which I cover this, then you just maybe need to go back and take a look at section 2.5 and make sure you know all of those 6 changes. So I'm just going to kind of review them with you real quick here. All right, so the first type of change you can have is a vertical shift. And remember, a vertical shift is when you add a number outside the function. So I'm going to underline both of those words. A number is added outside the function. So that might look like this. It might look like 2 to the x power and then plus a 4. Okay, so notice we already graphed what 2 to the x power looks like, right? So it's going to look just like the one that we just did, but we're just going to do what because of the plus 4 at the end? We're going to shift it up 4, right? Because it's at the end. Okay, so let's talk about the other type of shift we can have, right? A horizontal shift. Okay, now where was the number added to be able to know that we needed a horizontal shift instead of a vertical one? Inside. So this will be a number added inside the function. So remember, this one's the oddball, right? Why do I say that? Yeah, it goes opposite in the direction of the sign, so I'm just going to say opposite sign. So that's how you tell that it's a horizontal shift that's going to need to occur. So let's look at what that would be. If you had 2 to the x plus 3 power, so make sure you write that the way I did, right? X plus 3 is in the exponent spot. So notice, unlike the example from number 1, right, the 4 is not added at the end, it's added where? Like inside the exponent, right, inside the function. So this would actually shift it not right, but what? Left. Okay, so y'all remember what came next back in 2.5 and when we talked about it the second time, actually. After shifting comes what kind of changes? You remember? The hardest ones were we did at the end. The stretches and shrinks we did at the end, right? So what was after the shifting? Reflections, yes. So we can have a reflection over 2 things, right? We can have a reflection over the x-axis. Okay, so do y'all remember what used to tell us that we needed to do this? Negative sign where? Good, yeah. It's a negative sign outside the function or in front of. So I'm just going to underline the 2 most significant parts there. There's a negative outside the function. So that might look like this. Okay, notice I switched to the other graph from before, right? The one that we did in green. But because that negative sign is outside / in the front, it tells you to reflect over the x-axis. All right, so not surprisingly, the next one's going to be what? Flex over the y. Okay, so what's the difference between this one and the x? Instead of the negative sign being outside, where will it be? On the inside. And in this case, inside means in the exponent itself. So that might look like something like this. Instead of the 1/2, or sorry, instead of the negative going to the front, notice where it is this time, right? It's actually a part of the exponent itself. It's within the function. So because it's within the function, this is a reflect over the y-axis. So hopefully that's just kind of a review for you. Remember, these last two were usually the most challenging. So again, you might want to review that back in section 2.5 if you need to. But remember, a vertical stretch or shrink just means you're making the graph taller or shorter, right? So vertically changing the height of it, in other words. So do you remember what used to tell us to do this versus the other one? So there's a number being, instead of added, it's being multiplied, but where is it at? Do you remember? It's either to the front or, quote, outside the function. So this will be a number multiplied outside the function. So I'm going to underline those two words. So let's look at one like that. So what if I had you describe for me the graph of 3 times 2 to the x? Just to make sure that we're clear, if you're tempted, this is not the same as 6 to the x. You're not allowed to do that because the order of operations says you're supposed to handle exponents before you multiply. So that 2 to the x power should not be combined with that 3. You would literally leave it as 3 times 2 to the x. So if you're tempted to simplify in that way, you're not allowed to do that. But what this 3 actually does what? It vertically stretches this by a factor of what? Factor of 3. So what's maybe a everyday way to say that? It's going to be 3 times what? 3 times taller, right? What if it were 1/3 instead of 3? We're not going to do another one, but what if it were 1/3 instead of 3? Instead of making it 3 times taller, what would it make it? 1/3 is short, yep. So then the last type of change we can have is, of course, a horizontal stretch and shrink. Remember that horizontal changes are always what I call the oddballs. They don't really follow the rules. Remember, the shifting goes in the opposite direction of what we might have thought, and here we stretch or shrink maybe the opposite way of what we might have thought. But how you know you need to do this is there's a number multiplied inside the function. Okay, and I'm just going to give us a clue here. It's opposite of the way you might have thought. So what looks like a stretch will actually be a shrink, and vice versa. So if I ask for you to describe me this graph, 2 to the 3x power, notice how it's different from example 5, right? Example 5, the 3 is on the outside, right? Where's the 3 this time? On the inside, okay? So this would actually be a horizontal shrink, because remember it works opposite of the way we might have thought by a factor of 1/3. In other words, it's 1/3 as wide. Why is it width now instead of height? Back in example 5 it was height, so why is it width now in example 6? Because it's a horizontal stretch and shrink, right? So we're talking about how wide it is or how narrow it is. Okay, so let's maybe try one where you just have to maybe describe what the changes are. And we're going to stick with 2 to a power just because that's one that we've already graphed today. So maybe without graphing, let's see if we can describe the graph of h of x equals -2 to the x plus 2 power minus 4. So first we're going to break down what the changes are, and then we need to remind ourselves what order we're supposed to do these changes in case you do have to match this up with a graph on MyLab or something. So remember, when you're trying to decide what the order is, just work from the inside out. So start here. Notice this is the most inside of the function you can be, right? So what kind of shifting would this be? This would be a left 2. So I'm going to put a 1 here. That would need to be our first change. And again, if you're working from the inside out, what should come next? Which part should you tackle next? A -2. Okay, notice where it is. Is it outside or is it inside? Inside would mean in the exponent itself, right? And it's definitely not there, right? So it's to the front / on the outside. So this would be a reflect over what? Other one? X. Okay. When it's inside, it's Y. When it's outside, it's X. And then last but not least, what would the -4 tacked on the end of the problem do? Down 4. Okay. So in other words, this is what the graph is going to look like. It's going to look like the graph of the one that we did at the beginning of class. Okay, so it looks like the graph of y equals 2 to the x power, the blue graph we did at the beginning. But we would shift left 2 units, then reflect it over the x-axis. And finally shift it down to 4 units. Okay, remember order does matter, and a good rule of thumb is you just work from the inside outward. Okay, now this example only has how many different types of the 6 reflections in it? Only 3 of them, right? So just make sure that you know how to do the others also, but I don't want to do a whole lot of examples because I feel like this should just be a relearning of something we've already done twice before, actually. Okay, back in 2.5, and then again when we talked about rational graphs and stuff like that. Yes?
So if that exponent would have been there, but like let's say that there was a parentheses, like it was -4, like +2, like that was in parentheses, would you do the exponent and then move to the parentheses?
So, I'm not sure I know what you mean. You might have to write it. Like, what do you mean by
like, okay, so if it was that same thing, but
yeah.
then at the end it was like -4, like +2 at the end or something like that.
It won't do that.
And then that was like, if that was in parentheses.
It won't ever be like that. You would just need to simplify this first.
Okay.
If you had this, you would simplify this.
So you won't get an exponent and something in parentheses like all of the.
Not at the end.
Okay.
You might get like a parentheses up in the exponent or something,
Okay.
but yeah, you won't get it at the end. If you got something like this, you would need to work that out ahead of time. So, and if you're asking if it'll ever combine 2 different types of exponentials together, definitely not.
Okay.
Yeah. So, the examples that I showed here and the combinations of those is pretty much all that you'll have. Okay. So when we talk about exponential functions, there is a special type of exponential function involving a variable. It's not really a variable, a constant e that's on your calculator. It's not a variable because variables mean that the value changes, and this value is set in stone. So there is something called e, and it's called the exponential constant. So the value of it is 2.718281828, and then the 1828s keep repeating over and over and over. And E is not a weird value that somebody came up with to try to be difficult with us. Okay? E is the value that occurs with exponential growth. Okay, and there are lots of things in the world that grow exponentially. One of them is sickness, okay? Viruses like the flu, like COVID, okay? They grow exponentially, but also like bacteria. The population of any location usually grows exponentially. In other words, if all of y'all have 2 kids, but then your 2 kids each have 2 kids, and then your grandkids each have 2 kids, do you see that after a while the population is like exploding? That is why bigger countries like China have limited the number of kids that a family can have, because they can't control that explosive exponential growth. Not saying I agree with it, I'm just saying that's why they've decided to do it. So E is just that number that always comes up when you try to describe how quickly things are changing that are growing really, really rapidly. So without graphing it, I want us to think about how e to the x power would look if we were to graph it. Okay, and I say we've already graphed kind of a close version of this already today, right? So which one would be really, really close to what this e is that we've already graphed today? The 2 to the x, right? So it'll be the same shape as y equals 2 to the x, but with what change? So if you go back and look at that graph, I wrote something under there. Remember I said the bigger the base, the what of the curve? What happens to the curve when you increase the base? It gets steeper, right? So I'm going to say a little steeper, and why is it only a little steeper? Yeah, it's just a little bit bigger than 2, right? So I'm going to say E is just a little bigger than 2. But the general shape for what that E graph would be really, really close. Okay, so one way that we use E is when we talk about something called compound interest. So I mentioned things like viruses, bacteria, population can grow exponentially. Well, actually, so can your money if you invest it in an account that pays compound interest, because the word compound means that it's going to be compounded / get bigger and bigger and bigger as time goes on. And notice that's a more pleasurable form of exponential growth, right? We would want our money to grow exponentially. That's actually something pretty positive. So there are 2 formulas that we use when we talk about the interest that an investment can earn. And one of them looks like this. So I'm going to read that to you, and then we're going to talk about what all the variables mean. So A equals P times parentheses 1 plus R over N, and then raised to the NT power. A, off to the side, let's write down what everything is. A stands for the accumulated amount. That's why it uses the letter A, but it's basically the amount after time t. P is something that we call the principal, but that's just a fancy way of saying the starting amount. So you have some starting amount, it's going to get interest added to it, and you're going to end up with a hopefully higher ending amount. What do you guess R is if we're talking about money and interest and all that? Yeah, R is rate. It is as a decimal though, so let's underline that. Okay, so how do you change like a percentage rate to a decimal rate? Well, that won't change it to a percentage or from a percentage. That'll change it from a decimal to a, yeah, move the decimal twice, yeah. Your calculator really just moves it from a decimal to a fraction, not really from a percentage to a decimal. But we do move the decimal place 2 times. In other words, if it's 8% interest, what decimal should we be using? 0.08, not 0.8, 0.08, yeah. Okay, and then T is going to be time. For money, it's always years. But when we get to some equations for things like bacteria growth or disease growth, for instance, that time can definitely be lesser than that. But for money, we always figure it in years. And then N is probably the only one that's not necessarily obvious. This is the number of times per year that interest is compounded. Compounded is just a fancy way to say how often the interest is figured. And the reason that's significant is because we don't make payments on everything once a year, right? We're much more likely to make payments on a, a periodic timetable. So that's the first formula. The second formula, I call it the PERT formula, but make sure you write the R and the T in the exponent spot. So it's A equals P times E raised to the RT power. So I call it PERT just because that's the order of the letters, but make sure again that the R and T are in the exponent. And this is a special formula that you only use for what we call continuously compounded interest. In other words, there's not a time frame on it, it's just always kind of being figured. Have y'all ever looked online at like something that's being counted up and it's just like always turning, okay? Like have you ever looked, you probably should sometime, have you ever looked at like the national debt? If you look up what is the national debt right now, it won't tell you a dollar amount because it can't, because every second the national debt is changing. So it actually shows you like a moving target and it'll count it up, okay? Or like have you ever seen a timer where it's like always counting down like fractions of a second, something like that? So that's what it means to continuously compound. It's just kind of always adding fractions of cents to the interest as we go. So before we look at some examples here, you are going to need your calculator. So if you have it, go ahead and get that out. But here is a general principle of finance. The more often you compound or figure interest, the more money is earned. So if you only compound the interest once a year, you're going to earn less money than if you compound the interest every week, okay? So it's going to make a difference because the interest is just being figured and adding to more and more and more times. That's the difference. Okay, so we're going to use some heavy calculator problems, but I want you to find the amount in the account after 6 years if you invest $10,000 at 7.5% compounded. First, let's do monthly, because a lot of the things we pay for are monthly. All right, so we have two compound interest formulas. We have the first one, and then we have what I call the PERT formula, okay? But we only use the PERT formula for what kind of compounding? I underline the word even. Continuously. So if it doesn't say the word continuously, we're not using PERT, we're using the first one instead, okay? So we are going to use this formula, and then we're just going to figure out what goes where. So it's P times 1 plus R over N to the NT power. All right, so let's go ahead and plug in what we have versus what we want, right? What we want is A, right? That's what we're trying to find out. Okay, so what goes in for P? P is the what? The starting amount of money, right? So what was the starting amount of money? 10,000. So we're going to put 10,000 in for P, and then we're going to have a parentheses, and then it's going to be 1 plus. Okay, so here's where we need to be careful. If you have to, work it off to the side. What is your rate gonna be if it's 7.5%? Don't put 7.5. It's actually gonna be what? 0.075, okay? If you put 7.5, that means 750% interest. Okay, so remember you have to move the decimal place how many times? 2, okay? While we're here, let's go ahead and figure out what N is. N is always how many times a year we're compounding, right? Well, if we're compounding monthly, how many months are in a year? 12, so N is just gonna be 12. So let's plug it into the formula. So it's 0.075 over 12, and then raised to that same 12 times 6 years power. So let's use our calculator and figure out what that is. Move it up a little bit. Try to stay out of the glare if I can. All right, so 10,000. Move it down here. I think it'll be better. Trying to keep it in the light without having a glare, which is kind of hard. Times, use your parentheses, 1 plus 0.075 divided by 12. Close the parentheses. And then raise that to the 12 times 6 power. Okay, so if you have a calculator, it's nice if you'll work it with me just so you can see if you're going to get the right answer. Now, before I press enter, I shouldn't get something that's like really wildly more than 10,000, right? Because remember, realistically, 7.5% is decent interest, but it shouldn't get us, you know, a ton more. So notice that we get, rounded to the nearest penny, $15,661.17. Okay. If you have an older calculator, by older I mean like an 83, you will need to put parentheses around the exponent. You'll need to say, I want 12 times 6 to be all in the exponent spot. Okay. If you don't, you're going to get an answer like 70,000 something on this one. Okay. Why would 70,000 probably make you pause and think something's up? Does 70,000 seem like a reasonable jump from 10,000? It's not, right? If you got that kind of increase, a lot more people would be saving more of their paycheck than they do right now. So just kind of keep that in mind. Make sure your answer seems reasonable. All right, so what if I change it to daily? Okay, notice that I'm still not saying continuously, so I still need to use this same formula. And notice my rate didn't even change, right? My rate's still 7.5%. But what would N be this time? There's not only 12 days in a year, right? Yeah, it'd be 365. Okay, and we'll talk about some other frequently used compounding periods too. But for daily, that's what we get. So notice we're going to do the same thing. So it's going to be A equals 10,000 times 1 plus the 0.75, but this time over 365, and then to the 365 times 6 power. Okay, so let's see if we can get that one. So it'd be 10,000, make sure you do the right number of zeros, times 1 plus 0.075 divided by 365, close parentheses. Sorry, I'm in the glare. And then raised to the power of 365 times 6, because it's still 6 years, right? That part hasn't changed. What? All right, so if you make a mistake, sometimes you'll get a weird answer like that. So notice what I did here. I didn't put a plus sign, right? So you can, when you notice you made a mistake like I just did here, you can go second enter, and then you can use your arrows to go back and edit, because all I really need to do is insert a plus sign there, and now it looks right. Okay, so that can be something helpful if you don't want to start from scratch, right? I knew where my mistake was, so I just went back and edited it. You do second enter, and then it allows you to make an edit. So notice we make a little bit more in this kind of account. It shouldn't surprise us that we made a little bit more. How come? What did I say happened to interest the more often you compound it? There's more money, right? So it's not a crazy amount of more money, but I mean, it's $21 and something cents, right? So that's a little bit more. All right, so what about, lastly, if I ask you about continuously? Notice this is the first time I use this word, right? Continuously is the only one that uses a different formula, okay? So what's the formula that I need to use this time? The PERT one. So P times E to the RT power. Notice that's a smaller formula. It's actually nicer and quicker to use. So that means I'm going to have A equals the 10,000 and then E raised to the 0.075 times 6 power. So I just wrote parentheses there so that you would know that that's being times by 6. So your E button, if you have a TI calculator, is on the left-hand column. So you just need to find that E button. So we'll do 10,000 times, and then we'll go E to the power of, and then we're going to tell it we want 0.075 power times 6. And so notice this is, again, not crazy more. But notice this is the most money yet. And why is it the most money yet? Yeah, because continuously is even more often than daily, right? So it's more and more and more frequent, in other words. So some other N values, I don't want to do any more of these. I want you to practice these on your calculator. Okay? You don't need a graphing calculator, by the way. You just need a scientific calculator that lets you do exponents. That's really all that you have to have. So scientific calculators are pretty easy to come by. Okay? So some other ones that you might see quarterly. So if interest is compounded quarterly, what would N be?
2.
Nope. 4. Yeah, quarter literally means 4 times a year, right? So yeah, N would be 4. Okay. Another one you might see is weekly. Let's see if we remember how many weeks are in a year. Some of my other classes forget. 52. Yeah, it's not 48. 52 days in a year. Okay. What if it's annually? That's not very interesting, but how many times a year is annually? Just 1, right? Semi-annually, on the other hand, if you're a shopper and you're looking for the semi-annual sale, how many times a year is that? Twice a year. And then I'll do one more just because a lot of times people get paid bi-weekly, which means every 2 weeks. Okay, so what would that be if it was every 2 weeks? 26. Okay, so in your homework you might get some of these other terms thrown at you, and the only thing that it changes is what N is, right? So if you see any of these words, we use the first formula. When's the only time you actually use that second formula? If it says continuously, it'll come right out and say it. You won't have to guesstimate or anything like that. It always says it. Okay, and then just before we move on to the next topic, make sure also with this unit that you know your exponent rules, because these are exponential functions. So there are 3 exponent rules that we talked about during the first week of class. And we're going to probably be using these coming up, so I want you to remember what they are. Okay. So they were called the product rule. Do y'all remember the second one now that I told you the first one? Quotient rule. And what was the third one? Do you remember? The third one was the power rule. Okay, so I'm just going to briefly remind you of the rule here. The product rule, remember the word product means what operation? It means multiply. So it's for when you're doing some base to a power times the same base to another power. Okay, so how do you handle those types of things? What do you do with the exponents to combine them together? Add the exponents. So we add the exponents here. Now, by the way, that has to be, it's only when the bases are the same. Okay, so like you'd have to have the same number for the base or the same value for the base. What about quotient rule? What operation or what kind of math is quotients? Division. So this would be like if you were doing b to the x divided by b to the y. So do you remember how you combine those? You do subtract. So it'd be b to the x minus y power, so you subtract the exponents. And then lastly, the power rule is for when you have a power raised to a second power. So like think of like x squared, but then raised to the fourth power or something. What do you do with those exponents? Do you remember? You multiply them, so that's a multiplication dot there. So it's definitely going to be helpful if you remember these rules moving forward for how you combine different types of exponents.